Caffeine is an organic molecule that nearly everyone will consume at some point in their lifetime. It acts as a central nervous system stimulant, which causes an increased heart rate and increased alertness. This happens because caffeine has an extremely similar structure to adenosine, causing it to bind to some of its receptors inside of the brain. This causes delayed tiredness or a temporary feeling of alertness. Caffeine is similar to this portion of adenosine because it has a double ring structure. Next, caffeine's IUPAC name is 1,3,7-trimethylpurine 2,6-dione. Next, we'll talk about some of caffeine's functional groups and their properties. Caffeine has two amide groups on the right-hand side of the molecule. They are both tertiary amides because they are both bonded to 3 carbons each. Also, unlike amine groups, they are less basic because they do not have full control of their electrons due to their delocalized pi orbital system caused by resonance. Next, these amide groups contain a special type of resonance called zwitterionic resonance that occurs because the two amide groups are double bonded to each other. Next, there is one amine group in the lower left-hand corner of this molecule. This group is slightly basic because of its lone pair of electrons that are present on this nitrogen. Also, this amine group has the ability to hydrogen bond, increasing caffeine's solubility in polar solvents such as water, also elevating its boiling point. Next, in the center of the molecule, there is one alkene group, which consists of a carbon-carbon double bond. This changes the hybridization of the carbons bonded together from sp3 to sp2 hybridized. Lastly, this molecule contains two carbonyl groups. These groups create a polarity within the molecule, causing an increased melting and boiling point. Also, due to oxygen's electronegativity, there is a partial positive charge on the carbon and a partial negative charge on the oxygen atom. Let's talk about the hybridization of each atom. So this carbon right here is sp2 hybridized because it has 1, 2, 3 centers electron density, giving it sp2. This nitrogen is sp3 hybridized because it has 1, 2, 3, 4 centers electron density because of this lone pair that's not depicted in this. Next, this carbon is sp3 hybridized because again it has 4 centers electron density. This carbon is sp2 hybridized because of the 3 centers electron density. This oxygen is sp2 hybridized. This nitrogen again is sp3. This carbon sp3. This carbon sp2. This oxygen sp2. This carbon is sp2 hybridized again. This nitrogen is sp3 hybridized. This carbon is sp3 hybridized. This carbon is sp2 hybridized. And this nitrogen is sp2 hybridized. Next, let's talk about the electron geometry. All the sp2 hybridized atoms have trigonal planar electron geometry, and all the sp3 hybridized atoms have tetrahedral electron geometry. Next, let's talk about the intermolecular forces in the molecule. There are 3 types of intermolecular forces contained within this molecule. There are London dispersion forces, which are present in all molecules, which are the weakest forces, and they're also called van der Waals attractions. Next, there's dipole-dipole attractions, which occur because the molecule is polar. And lastly, there are hydrogen bonding forces, which occur between hydrogens and nitrogens. Next, caffeine can form a resonance structure by bringing this lone pair of electrons up onto here, and this bond of the oxygen up onto the oxygen. Also, this happens down here. This causes a positive charge on the nitrogen and a negative charge to occur in the oxygen. Also, the zwitterionic resonance is present in this diagram because of the aromatic ring formed in the product. Lastly, caffeine has 8 chemically distinct carbons. Let's show them. 1, 2, 3, 4, 5, 6, 7, and 8. Each line in the C13 NMR spectra displays a distinct carbon. Also, the further downfield the peak, the more deshielded the nucleus is, because it is easier to flip the nucleus and cause it to resonate. An example of this is an example of the carbon on the carbonyl groups. The 3 carbons that are lowly deshielded in spectra are the 3 methyl groups.